Next time you step outside, take a quick look up. Stretched across the sky, connecting cities, and literally powering our modern world are endless miles of transmission lines. But have you ever stopped to wonder what exactly is inside those cables? What kind of hidden engineering actually allows them to carry massive amounts of electricity over huge mountains and through fierce storms?
Well, welcome to today's Explainer. We're going to go ahead and crack open those overhead lines to analyze the intricate cross-sections of 7 distinct transmission line conductors. Let's dive right in. Here is our quick roadmap for today. First, we'll meet the conductors, then cover the uniform metals, move into the aluminum foundation, check out how they're reinforced for strength, and wrap it all up with the high-tech HTLS. All right, part 1. Meet the conductors, a cross-section view.
Engineers don't just use a massive, solid block of metal for these wires. That wouldn't work. Instead, they rely on these multi-stranded structures, winding smaller wires together to build a thicker, flexible cable. And as you'll see, there's a clear evolution in complexity from standard metals up to some highly engineered composites.
The big takeaway here is that we have exactly 7 distinct types of conductors in our toolkit today. Not just one standard wire, but 7 totally unique solutions. Each one is custom engineered to solve specific power transmission challenges, whether that's managing cost, weight, distance, or even extreme heat.
Section 2. The uniform metals, featuring copper and galvanized steel.
Before we jump into the really complex composites and alloys, we need to ground ourselves with the basics: copper and galvanized steel. These absolutely stand out because they are built from foundational, uniform metals all the way through their various stranded layers. The contrast here is honestly pretty striking. The copper conductor has that unmistakable, distinct reddish-orange hue and a really tight stranding. Right next to it, the galvanized steel conductor is a uniform industrial gray. Notice how its thicker, robust strands almost look less like something that carries electrical current and more like a heavy-duty structural cable.
Moving on to Section 3. The aluminum foundation, AAC and AAAC.
Now let's look closely at these two. They share a very similar silver-gray, tiered, multi-stranded structure. At first glance, they look almost identical, don't they? Both of them are capitalizing on the fantastic lightweight properties of aluminum as their core foundation. Let's demystify these acronyms, starting with AAC. This one stands for All Aluminum Conductor. It's exactly what it sounds like. This represents the pure baseline material. Just straight, pure aluminum wires stranded together layer by layer to form the cable.
Next up is AAAC, which is the all-aluminum alloy conductor. The absolute crucial addition here is that one word, alloy. It seems like a subtle change in the name, but trust me, it is a massive change in the actual chemistry of the metal.
When you compare them side by side, you can really see how engineers iterate on a fundamental design. By upgrading pure aluminum into a stronger alloy, they extract far better structural performance out of a cable that, visually anyway, looks totally identical from the outside. Section 4. Reinforce for strength, looking at ACSR and AC car. So as these lines have to span greater and greater distances between transmission towers, the sheer physical weight of the cable becomes a massive engineering challenge. Pure aluminum simply isn't strong enough on its own for those huge gaps. It would just break. That is exactly where reinforced composites come in. Notice how one of them even features a heavy-duty bolted ring clamp, which is a perfect reminder of how these rugged cables are physically suspended high up in the air. Let's break down ACSR. This stands for Aluminum Conductor Steel Reinforced. This specific design relies on a rugged steel center to act as the muscle. That steel carries the immense physical weight of the line over a long span, while the outer layers of aluminum handle the actual job of conducting electricity. Now, contrast that with ACACR, or Aluminum Conductor Alloy Reinforced. Here, the reinforcement strategy completely shifts. Instead of using heavy steel, engineers opted for an inner core made of a high-strength aluminum alloy.
The sheer brilliance of both these designs is that they keep the highly conductive aluminum exactly where it needs to be, on the outside. They're just swapping out the inner core material to solve different structural puzzles based on weight and distance requirements.
All right, Section 5, the high-tech HTLS, which is complexity in action. Take a second to just marvel at how vastly different and multi-layered this final conductor looks compared to the first 6. We're definitely not looking at uniform metal strands anymore. This is highly specialized engineering designed for absolute extremes.
HTLS stands for High Temperature Low Sag. It's a highly specialized name that hints right at its advanced thermal capabilities. Here's the thing. When power lines carry a massive amount of current, they heat up. And when traditional metal lines heat up, they expand and sag toward the ground, which is incredibly dangerous. HTLS is engineered specifically to withstand very high temperatures, so it can carry much more power without that hazardous sag.
Check out the visual complexity here. Beneath those familiar gray metal strands on the outside, there's a striking yellow and black banded layer, which is then followed by a thick, smooth white inner sheath wrapping a central core. It's an absolute massive leap in complexity, utilizing advanced composite materials to fight off thermal expansion and push vast amounts of electricity through the exact same physical space. Bringing it all together, we can really see the full evolution. We started with the pure AAC and the upgraded AAAC. We explored the structural muscle of ACSR and ACAR alongside the foundational copper and galvanized steel. And finally, we uncovered the cutting-edge technology of the HTLS. It's an incredibly diverse toolkit that modern engineers use to build the grid that actually keeps our lights on.
So I'm going to leave you with this provocative thought to chew on. Now that you know the hidden anatomy of our electrical infrastructure, take a look outside. Which of these 7 conductors do you think is hiding inside the power lines right outside your window right now? Thank you so much for joining me for today's explainer, and stay curious.